In this video, I'll introduce the final project of Introduction to Computer Science I've done with my teammate Yuping Zhang. We created a game called Crazy Arcade using Pygame. Here's the agenda of this video. I'll first walk you through the basic rules of the game and talk about our working process with several highlights. In the end, I will talk about some reflection and further improvement of the project. Our inspiration comes from a game called Q 版泡泡糖 on China's most popular game website, and we adapted it into a human-computer game with artificial intelligence. The game contains two players, a human-controlled agent and a machine-generated agent, and there are several varieties in landform. For example, there are various blocks that can be destroyed by bombs, and walls that forever exist. Now let's have a quick view of how the game works. The little person in blue, as you can see in this video, is the machine-generated agent. All of its movement and bomb placement are automatically generated by the program itself. I'll go into the details of the decision-making framework of the machine later in this video. We've also set 3 difficulty levels for the game. Different difficulty levels simply imply different parameters for machine simulation, which decides how intelligent the machine is. The human user in our game would be able to use mouse click and keyboard control to play the game. This is the steps we took in gradually building up the whole game. First, we built up the whole game setting with a human-controlled agent, and then we gradually added a machine-generated agent with more and more intelligence and empowered it with a smart decision-making framework. In the end, it could react to activities of the human-controlled agent and some urgent cases as well. This is where the whole thing begins, the very first state machine diagram that we drew to set up the whole game and a human-controlled agent. Then we decided to handle our location-based game by an underlying landform matrix at the back and a Pygame window at the front. As these two layers intermittently interact with each other, both the game page displayed to the user can be the most updated version, and the machine-generated agent can listen to the underlying landform and make intelligent decisions based on that. The decision-making framework for the machine-generated agent consists of 2 parts, movement event and bomb placement. It's movement based on random walk, and the machine is pretty risk-averse that it avoids danger regions. It's bomb placement based on a given probability, and it runs 100 times of simulation of 7 future steps and evaluate if it should place a bomb without killing itself. The radar chart at the bottom pretty much describes the characteristic of the machine player we designed. It's super sensitive to potential dangers, good at predicting futures, and has extremely low tolerance of wrong decisions. One of the key challenges when we build this program is that the overlapped bombing event lead to chaotic dynamics in landform change, which makes the machine extremely hard to identify safe locations on a real-time basis. Fundamentally, it's a problem of dynamic time warping between landform change and machine evaluation. So our solution is to embed certain urgent response mechanism when potential landform change is detected. Here comes the first core function of the machine's urgent response mechanism. This in-dilemma function returns a balloon value that indicates a machine player's status if it is trapped in the danger zone with 0 adjacent exit options among 4 directions. If it returns true, it will initialize a more aggressive and blind exploration in larger region to escape. Next function is called urgent move, and it handles real-time reaction to possible attacks from human player. If a bomb is detected, machine player would first follow a relatively safe trajectory sampled from 20 preset adjacent exit options, and then escape further if necessary after evaluation. There's another function called survive. It performs an aggressive, which means risk-neutral, and blind search in a large region in hope of wandering to a safe position. This function adds to the random walk, and is limited by movement speed and maximum survival chance depending on difficulty levels. Let's watch a video that demonstrates the urgent response mechanism of the machine player. The little person in blue, as you can see in this video, is the machine-generated agent. Here's a diagram explaining our use of simultaneous multi-threading in the whole program. At global level, the human-controlled agent functions in the main thread, and the machine-generated agent functions in the sub-thread. Regarding all bomb events, bomb explode and bomb release are all packaged in a sandbox environment and built into the remaining program as child threads. In a simulation evaluation, the init number of processes is up to 10. Finally, we integrated the whole program into a chat system as a sub-process. Here are the codes that help us realize the simultaneous multi-threading. The last highlight is Monte Carlo simulation. This simulation helps the machine to determine whether to place a bomb at a given location. In each iteration of simulation, the program would create a virtual machine agent by itself and perform the random walk. We run the simulation for a large number of times and record the probability that the machine encounters dilemma within limited steps. Finally, we compared this estimated probability with a preset threshold to return a balloon value. These are the two most important functions that handle the simulation. Thank you for watching the video, and we would like to further improve our program in the following perspectives. Like adding more aggressive algorithms to the machine player that it can actively attack the human player. And through reinforcement learning, the machine agent can be more adapted to given landform and thus perform more effectively. Last but not least, if the machine can play with itself and learn from childs, it would become much more powerful.